Hello everyone, we are from Group 3 in Electromagnetic Field Theory. We would like to do a presentation about Faraday's law. But before we get into the topic, we have a little disclaimer. This video presentation is merely for educational and informational purpose. It is not intended as a substitute for professional practice. Should you decide to act upon any information on this video, you do so at your own risk. Now, we are moving to the introduction of Faraday's law. Enjoy!
Now we have conductor loop and a magnet. The magnet will create a magnetic field around it, which flow from north to south poles. So now let us exert a force to move the magnet downwards. We can notice that at the moment when we're moving down the magnet, a current will be flowing through the conductor. This phenomenon can be explained by the Faraday's law of electromagnetic induction, which states that a current will be induced in a conductor which is exposed to a changing magnetic field. By using the right-hand grid rule, where the thumb represents the magnetic field and the finger represents direction of current, you can notice that there will be a magnetic field produced in outward direction. It is in opposite direction with the initial magnetic field as we move down the magnet. This behavior can be described by the Lenz's law of electromagnetic induction that states that the direction of this induced current will be such that the magnetic field created by the induced current opposes the initial changing magnetic field which produced it. However, there is no current induced when we keep the magnet in the same position. Hence, the Faraday's law states that a static magnetic field produces no current flow. And similarly, a current will be produced when we move out the magnet, but the current will be moved in an opposite direction. And by applying the right-hand grid rule, we can know that the produced magnetic field is opposed to the changing magnetic field, which is in line with the Lenz's law. The voltage will generate a current flow. In this example, we can say that the current is produced when we apply a force to change the position of the magnet so that the magnetic field will be changing. Hence, Faraday's law has stated that a time-varying field produces an induced voltage, which is also called as the electromotive force or simply EMF, that causes a flow of current. The equation of EMF is given as below, where the lambda is the flux linkage, n is the number of turns in the circuit, and phi is the flux through each turn. The negative sign indicates Lenz's law, that the induced voltage acts in such a way as to oppose the flux producing it. Now let us consider a region of magnetic field where a surface is placing on it. By considering the magnetic field is increasing, a current which is produced by the induced voltage will be flowing through, and the direction can be determined by using right-hand grid rule. And previously, we have determined the EMF equation, and in this example, we assume that n equals to 1. By observing the figure, we can see that the induced voltage is actually caused by the changing magnetic flux due to the magnetic field on that surface. And hence, we can also express the EMF formula like this. Faraday's law states that the absolute value or magnitude of the circulation of the electric field around a closed loop is equal to the rate of change of magnetic flux through the surface enclosed by the loop. Hence, we can express the EMF formula as follows. And remember that although the static electric field are conservative field, but the electric field produced by a changing magnetic field is a non-conservative field. The variation of flux with time may be caused in three ways. The first one is by having a stationary loop in a time-varying magnetic field, which I have shown in this example where the magnetic field keeps increasing. When we move the surface area, the flux passing through the surface was also changing. Hence, the second one is by having a time-varying loop area in a static magnetic field. The last one is the combination of the two methods above, which is by having a time-varying loop area in a time-varying magnetic field.
This is the first condition to generate time-varying flux. There's two ways to create time-varying magnetic field in a stationary loop or transformer EMF. First is move a permanent magnet in and out of solenoid. The moving bar with magnetic field surrounding it will induce EMF inside the coil. Higher the speed and the area of solenoid, higher the amount of induced current. Second is simply apply AC source to a transformer. AC source is time-varying supply. It will cause the change in current and hence fluctuate the magnetic flux. Next is about the generation of transformer EMF. Let's see, we have a coil as shown in picture like on y-axis. Then we have a magnetic flux moving in the positive z direction. Since the loop is stationary but magnetic flux changing over the time. So from the Faraday's law, we have the equation of V EMF equal to negative n d over dt integrate B dot ds. Since the loop wiring has constant area, hence now does not depend on the area anymore, and we now consider only the change of magnetic flux. So we have the equation as below. V EMF equal to negative n integrate del B over del T dot ds. The transformer EMF voltage is the voltage that would appear across terminal 1 and terminal 2, as you can see in the picture. Direction of EMF is determined by right-hand rule. In the figure, let's put our thumb upwards and then we can see the direction of control that represented by our four fingers. It shows the polarity of terminals. If you want to determine the direction of current, we can use Lenz's law, which states that the direction of induced current will oppose direction of change of magnetic flux that produce current. By referring to the figure that magnetic flux density moving at positive z direction, it will induce the current in the wire that moving in clockwise direction as shown. Because of the time-varying magnetic flux will generate an induced magnetic flux density opposed to changing V. The principle of induced magnetic flux density are similar to the principle of friction that oppose applying force. Since the direction of induced magnetic flux density are in negative z-axis, by using right-hand rule, the four fingers represent the induced magnetic flux density and thumb is the direction of current generated, and the direction of the current is clockwise. From electrostatic, we knew that V EMF equal to integral of E dot dl. Then we can equal the equation from Faraday's law. Hence, we will attempt this equation. After that, apply the Stokes theorem to the left-hand side. Then compare left-hand side and right-hand side. We can see clearly the curve cross E will equal to negative del B over del T, in which it shows the relationship between electric field intensity E and magnetic flux density B. From Figure 1, actually we can rewrite them into an equivalent circuit as follows. Transformer EMF can be represented by an AC source that we had two resistance, where Ri is the internal resistance of the wire. By using Ohm's law, we can obtain this equation. I equal to V EMF over R plus Ri. But for a good conductors, Ri usually very small compared to R. Hence, we can further simplify the equation as I equal to V over R.
Another type of EMF generation is motional EMF. Motional EMF is the EMF induced by a moving loop in a static magnetic field. Consider this example. A metal rod is placed on two metal bars that connects to a resistor. There is a static magnetic field and the direction is into the screen. Let's say the metal rod is moved to the right from its initial position at velocity u. The area of the loop that encloses the magnetic field increases. Therefore, the amount of magnetic flux enclosed also increases. Then, to oppose the increased magnetic flux, another magnetic field is induced and the direction is out of the screen. The induced magnetic field will then induce an EMF, which we call motional EMF. Then, using right-hand rule, the fingers other than the thumb point to the direction of B induced. We see that the thumb points to anti-clockwise direction. That is the direction of current induced. Then we have this equivalent circuit. We can also determine the direction of current induced with Fleming right-hand rule. Then, to come out with the equation, first, we know that magnetic force dF equals to dq times the cross product of velocity and magnetic field. Then, we have Fm equals to q times cross product of velocity u and magnetic field B. We also know that electrical force F equals to QE. Then we get EM equals to U cross with B. To prove the direction, take previous example. U is in positive X direction, B is in negative Z direction, and the cross product is the current in positive Y direction. Then, from this equation, VEMF equals to closed loop integration of E dot dl. We substitute EM into the equation, then we have VEMF equals to the integration of U cross B dot dl. It also has to be taken note that the direction of dl in the integration has to oppose to the direction of current induced.
Now we are at transformer and motional EMF section. Basically, we are combining a moving conducting loop from transformer EMF and a time-varying magnetic field from motional EMF. As you can see in the screen, the formula for VEMF is gathered from both of the EMF. The negative integral S delta B over delta T times ds is gathered from transformer EMF, while the integral L U times B times dl is gathered from motional EMF. The other formula is gathered from Stokes' theorem that we get for both EMF. The negative delta B over delta T is gathered from transformer and the other is gathered from motional EMF. Alright, that's it for our explanation. We are supposed to give an example about Faraday's law, but we are terribly sorry that we cannot provide you one because there is a problem in our group. But anyways, thank you so much for watching, guys. We hope that you are in good condition always, and see you next time. Bye bye.